There's a star that astrophysicists tend to avoid bringing up in public. Not because it's classified, not because the information is dangerous, but because it's deeply paradoxical, and science still doesn't have a satisfying answer for why it is the way it is. And scientists, as you might imagine, don't particularly enjoy admitting in public that something has them completely stumped. It's called Przybylski's star, named after Polish astronomer Antoni Przybylski, who first drew attention to it back in 1961. It sits in the constellation Centaurus, about 380 light-years away from us. Small, quiet. Nothing about it looks unusual from the outside. There are billions of stars like it in our galaxy, and most of them never earn more than a passing glance through a telescope. But when scientists pointed a spectrograph at it and read its chemical makeup from its light, something happened that simply shouldn't have happened. They found actinium in the spectrum. If your first reaction is, "So what?" then let me explain exactly why this is a genuine scientific catastrophe. Actinium is a radioactive metal. Its half-life is just over 21 years. Przybylski's star, on the other hand, has existed for billions of years. Do the math. Over the lifetime of that star, any actinium should have decayed trillions of times over and transformed into other elements long before the first bacteria appeared on Earth. There should not be a single atom of actinium left. Not mathematically, not physically, not in any way. And yet, there it is. And that's not even the whole story. When astrophysicists looked more carefully, they found other short-lived elements in the same star's spectrum, including polonium, radium, and protactinium. An entire collection of substances that have absolutely no business being there. This isn't a one-off anomaly you could chalk up to a measurement error. It's a consistent, repeating pattern. And it shows up every single time astronomers observe this star for more than 60 years running. Welcome to Ashes of Stars. Today we're covering element number 89, actinium, a metal that spent half a century successfully impersonating a different element, a metal that glows blue in the dark, that continuously produces the rarest element on Earth inside itself, and that today strikes cancer cells with more precision than any surgical blade. Get comfortable, because this is a long story, and I promise it won't be a boring one. So let's get back to our strange star. Science has two explanations for it, and both of them are equally uncomfortable. The first, somewhere inside that star, right now, certain super-heavy elements are decaying. Elements we haven't even discovered yet here on Earth. They would belong to what physicists call the island of stability. This is a region in the periodic table where, according to theoretical calculations, elements with around 124 to 126 protons in their nucleus should exist. Theory predicts that these nuclei would be significantly more stable than their neighbors in the table, possibly with half-lives lasting thousands or even millions of years. If such elements exist inside Przybylski's star and are slowly decaying, they could be continuously producing fresh actinium as a decay product, right now, without stopping. The problem is that we have never synthesized a single element from that region. The heaviest element ever created in a laboratory is oganesson, element number 118. It survives for a few milliseconds, and that's already considered a major achievement. The island of stability is still far beyond our technological reach. But if Przybylski's star is showing us evidence of its existence, that means something very significant. The periodic table is not finished. Beyond element 118, there may be a continuation we simply cannot reproduce yet. And that continuation appears to be sitting 380 light-years away, completely indifferent to our opinions on the matter. The second explanation is more of a scientific provocation, what some researchers call the last resort hypothesis. A few scientists, as a kind of extreme thought experiment, have floated the idea, what if the actinium ended up there because some advanced civilization is using the star as a nuclear waste dump? Before you roll your eyes, I'm just reporting other people's ideas here. Most astrophysicists treat this suggestion with barely concealed skepticism. Science has a working principle. As long as there's any chance of finding a natural explanation, nobody's going to blame aliens. But the simple fact that this idea was ever raised in scientific circles shows just how deeply this element has cornered us. When serious people in serious journals start discussing extraterrestrial garbage disposal, something is genuinely wrong with the object they're studying. We'll come back to the star at the very end because the way this story closes is worth the wait. But for now, let's come back down to Earth, because down here, actinium raises just as many puzzles. And those puzzles started from the very moment of its discovery, or rather, from the question of who actually discovered it and whether they really did. In 1899, in Paris, a young chemist named André Debierne was working in the laboratory of Pierre and Marie Curie. Close colleagues, one team, complete mutual trust. Debierne announced that he had found a new element in uranium ore. He called it actinium, from the Greek word for ray, because whatever he had found was intensely radioactive, and by his account, even glowed in the dark. Marie Curie backed her colleague, and the scientific world executed. The periodic table had gained one more entry. The discovery story seemed closed. But then, 3 years later, something interesting happened. Friedrich Giesel, a German chemist who made his living from the industrial production of radioactive materials and knew radioactive chemistry inside and out, ran his own experiments on the same ore. He found a radioactive element. He called it imanium because it released a radioactive gas when it decayed. We now call that gas radon, but the terminology wasn't settled back then. Scientists began comparing Debierne's data with Giesel's. The conclusion? It was the same substance. The question was, who had found it first? Debierne's date came earlier, 1899 versus 1902. The answer seemed obvious, but here's the catch. Debierne's data was vague. His descriptions of the new element's properties were imprecise, sometimes contradictory. Colleagues couldn't reproduce his results. Giesel's data, by contrast, was specific, clean, and reproducible. He characterized the element far more accurately and in far greater detail. Historians of chemistry still ask the uncomfortable question: did Debierne actually find what he thought he'd found? Or did he simply detect the presence of something new in the ore without being able to properly describe or characterize it? Priority was awarded to Debierne anyway. The element kept the name actinium, not imanium, and most historians of science agree that what tipped the scales wasn't an analysis of the data, it was something else entirely. Debierne was a Curie insider, working in her institute, operating under her academic protection. And the word of Marie Curie in European science at the turn of the 20th century carried more weight than any table of experimental results. This is a documented episode in the history of chemistry. It just rarely makes it into textbooks, where people prefer clean discovery stories over uncomfortable questions about how credit actually gets assigned. But here's what's even more striking. Even after the element was officially discovered, named, and being studied, nobody had actually seen it in pure form for nearly half a century. The first sample of pure actinium wasn't obtained until 1947, 48 years after its discovery. How is that even possible? Let's work through it. Actinium was hiding, and it was hiding behind a very specific element, lanthanum. It did this so convincingly that chemists spent decades confusing one for the other. Lanthanum sits at number 57 in the periodic table. Actinium is at number 89. Different periods, different atomic masses, different positions on the table. What could they possibly have in common? As it turns out, quite a lot. They have nearly identical ionic radii and very similar chemistry. In solution, they behave almost identically. They settle out together, crystallize together, respond to the same reagents. Separating them using the standard methods of the time was nearly impossible. The reason for this resemblance runs deeper than it first appears, and we'll come back to it. The short version, both elements have similar electron configurations in their outer shells, and it's that configuration that drives chemical behavior. Nature repeats its patterns at different levels, and actinium and lanthanum are one of the clearest examples of that repetition. For 48 years, chemists worked with what they called actinium. They published papers, built theories, measured properties. But in their flasks, the actinium might have been present in tiny amounts, while lanthanum dominated. All those measured actinium properties were largely the properties of an impurity. Actinium was wearing a mask, and it wasn't removed until 1947, when ion exchange chromatography arrived, a fundamentally more precise method of separating elements based on the way different ions cling with different strengths to a special material as they pass through it. The first person to see truly pure actinium lived in an era when the atomic bomb already existed. The Manhattan Project, which we've discussed before on Ashes of Stars, concluded in 1945. Pure actinium was isolated in 1947. An element discovered in the 19th century was finally obtained in pure form only in the atomic age. And then came the next surprise. Even after finally getting a pure sample, scientists ran into a problem nobody had really anticipated. Measuring its properties using standard methods turned out to be extremely difficult. Not because the instruments weren't there, but because the sample itself was getting in the way. Actinium's radioactivity was so intense that the background signal from its own radiation interfered with precise measurements. The instruments of that era weren't designed to handle that level of noise coming from the very substance being studied. Here is the paradox early nuclear chemistry ran into. The substance you want to study actively interferes with your ability to study it. Actinium was too radioactive for careful benchwork and too scarce to handle safely from a distance. The solution came with the development of remote manipulators behind lead glass shielding and more sophisticated detectors. But that took years. A detailed picture of actinium's physical and chemical properties took several more decades to assemble after it was finally isolated. An element discovered in 1899, isolated in 1947, and only fully understood by the 1960s and 70s. Nearly 100 years from discovery to genuine comprehension. No other element in the periodic table resisted science so stubbornly for so long. So what does actinium actually look like as a physical object? If you examine it on its own terms, behind an unremarkable appearance, you'll find things that don't quite fit the usual idea of what a metal should be. On the surface, a silvery white metal, soft and malleable. It looks a bit like aluminum or magnesium, at least in terms of shine and color. Its melting point is around 1050 degrees Celsius. Nothing exceptional there for a mid-range metal. But there's one feature about it that's very hard to forget once you know it. It glows blue in the dark. This is not a legend, not artistic exaggeration, and not a trick of the light. It's a real physical phenomenon called radioluminescence. Here's how it works. Particles ejected during the decay of actinium's nucleus ionize the air molecules around the metal, knocking electrons out of them. When those excited molecules return to their normal state, they release the absorbed energy as light. A soft, bluish, genuinely eerie light. The metal just sits there in the darkness, quietly glowing, with no electric current, no chemical reaction, no flame. A similar glow appears in the water surrounding the core of nuclear reactors. That famous blue shimmer you've probably seen in photographs if you've ever looked into nuclear topics. There it's called the Cherenkov effect, and it works through a slightly different mechanism. Charged particles travel through water faster than light can travel through water, creating a kind of optical shock wave. But visually it's very similar. The same cold blue hue, the same sense of something otherworldly. That glow is almost certainly what DIDN saw in his Paris laboratory back in 1899. In an era when radioactivity had only been discovered a few years earlier, that sight must have made an almost mystical impression. Picture yourself in his position, a dark Parisian laboratory, the gas burners extinguished, and suddenly a cold blue light stares back at you from a flask. No heat source, no flame. Just a substance glowing on its own. No wonder DIDN immediately wrote to Curie. I would have too. But the blue glow is just the beginning. Here is a fact that puts actinium in a completely unique category among all the metals ever held in human hands. If you gather just a few grams of actinium in one place, it will melt itself. No burner required, no external heat source, simply because its radioactive decay generates heat faster than the metal can release it into the surrounding environment. The critical mass at which self-melting begins is just a few grams, less than what fits in a teaspoon, a metal that melts from the sheer fact of its own existence. Let's go through exactly what's happening there, because this isn't just a hot metal, it's a fundamentally different kind of process. Actinium-227 emits alpha particles with every nuclear decay. An alpha particle is 2 protons and 2 neutrons flying together at enormous speed. These particles are heavy and charged, which means they interact intensely with surrounding atoms and slow down very quickly inside matter. All of their kinetic energy converts to heat in the process. Every single decay event is a tiny heat pulse. And it doesn't stop there. The decay products of actinium, thorium, radium, bismuth, and others down the chain are also radioactive. They emit radiation too. They generate heat too. Together, a small actinium sample with its entire radioactive family produces heat continuously, without fuel, without any chemical reaction, without any external energy source, simply because atomic nuclei are unstable and want to reach a stable state. This is the same principle behind the radioisotope thermoelectric generators that power deep space probes like Voyager and Mars rovers like Curiosity and Perseverance. Those typically use plutonium-238, which generates heat more slowly and in a more controlled way. Actinium is too rare and too intensely radioactive for that role, but the physics is identical. A substance that heats itself purely by existing. With actinium, the line between a material and an energy source blurs to the point where those two concepts almost stop being distinct. In theory, given enough insulation, a sample of actinium would reach its melting point and then keep going, all the way to 3,000 degrees Celsius, its boiling point, and vaporize. A metal that evaporates itself, without fire, just by existing. To understand why this happens, we need to look at something that rarely gets explained in plain language. Let me do that right now. When an actinium nucleus decays, it doesn't simply disappear. It transforms into a different element. Call it the daughter. The daughter is also radioactive, so it decays too, becoming a granddaughter. The granddaughter decays into a great-granddaughter, and so on down the chain. Physicists call this whole family the decay products. A slightly odd term, but accurate in the sense that each new element in the chain is literally born from the one before it. Think of it like a chain reaction in slow motion. One nucleus falls apart, and what emerges immediately starts falling apart too. Each collapse releases heat. Actinium-227 has a large and energetic family. The chain runs through thorium, radium, radon, polonium, bismuth, thallium, and lead, before finally settling into something stable. Every member of that family contributes heat. All of them together, generating it continuously, without pause, without fuel. This is why actinium is more dangerous than it first appears. You think you're working with one element, but you're actually holding an entire radioactive clan that lives inside your sample and has no intention of leaving. This is also why the world's total supply of actinium is never stored in one place. It's kept in microscopic quantities, inside specialized, shielded containers. It's handled remotely, through manipulators behind lead glass. This isn't excessive caution, it's a physical necessity. So where does actinium actually come from on Earth? Here we hit a fact that completely changes the idea of what it means for an element to exist in nature. Actinium didn't accumulate in the ground since the planet formed. You can't find it the way you'd find gold or coal, something that built up over billions of years. It's being produced right now, every second. And every second it disappears. Here's how the cycle works. Earth's crust contains uranium-235, the same isotope used in nuclear reactors. It decays slowly, with a half-life of 704 million years. Deep in the chain of that decay, through several intermediate steps, actinium-227 inevitably appears. It lives for just over 21 years before decaying further into thorium-227, which decays into radium, which decays further still. The process never stops for a moment. The result is an equilibrium. Actinium is produced from uranium at exactly the rate at which it decays. At any given moment, the Earth's crust contains a small amount of actinium. Not mountains of it, not ore deposits, but a microscopic quantity scattered throughout the rock, continuously replenished by uranium decay. As long as uranium remains in the crust, there will be actinium. And uranium has about 4.5 billion years left in it. Actinium isn't mined from shafts or extracted from ore in any conventional sense. It's isolated from uranium ores through chemical processing, slowly, laboriously, in microscopic amounts. 1 metric ton of uranium ore yields roughly 1/10 of a milligram of actinium. Less than a speck of dust. Less than what stays on your finger if you touch chalk powder. For comparison, 1 metric ton of ore from a rich gold deposit yields about 5 grams of gold. 5 grams against 1/10 of a milligram. A difference of 50,000 times. Gold seems rare, but next to actinium, it's practically lying around on the ground. There's another way to obtain actinium, one that's more unexpected and, in its own way, historically fascinating. Actinium-225, the most medically valuable isotope, is produced in nuclear reactors by bombarding radium-226 with neutrons. A radium atom captures a neutron and, through a short chain of transformations, becomes actinium-225. It sounds straightforward, but in practice it requires specialized reactors, custom irradiation containers, and complex separation chemistry. And the stockpiles of starting material in several countries are a legacy of mid-20th century research programs. American and Soviet scientific programs from the Cold War era left behind reserves of thorium-229, from which actinium-225 is also produced through natural decay. We are treating 21st century cancer with material born from the nuclear legacy of the 1960s. Cold War waste, repurposed in oncology clinics. History has an unexpected sense of humor sometimes. You might remember from the episode on lead how the body tries to isolate it by storing it in bones, away from vital organs. An imperfect defense, but a defense nonetheless. Some bacteria have developed ways to neutralize mercury. 4 billion years of evolution, and for nearly every toxic element, life found some kind of answer. Nearly every one, except one. Living organisms on Earth have spent 4 billion years evolving. In that time, they developed mechanisms for dealing with an enormous range of elements, using them, isolating them, excreting them. Lead, as mentioned, the body tries to tuck away in bones, far from critical organs. It's imperfect, but it's an adaptation. Certain bacteria can convert mercury into less toxic forms. These are the results of millions of years of evolutionary pressure, where organisms that could handle an element survived, and those that couldn't, didn't. With actinium, none of that exists. No isolation mechanism, no adaptation. Because in nature, actinium has never appeared in concentrations high enough to create any meaningful evolutionary pressure. Natural actinium is so dispersed throughout Earth's crust that in 4 billion years, life on this planet never meaningfully encountered it. And here is the problem. The body mistakes actinium for lanthanum, or sometimes for calcium, depending on the context. Enzymes that work with lanthanum in cellular processes pick up actinium instead. They can't tell the difference. The ionic radius is similar, the charge is the same, the chemical behavior is close enough. Actinium gets incorporated into proteins, into enzymes, into cellular structures. And it turns those structures into radioactive objects from the inside. The biological system doesn't receive a distress signal. It receives what it thinks is a normal building block. And only afterward does it discover that this building block is firing from within. This isn't a slow accumulation process like with lead. It's immediate integration into the cell's working machinery. Evolution did not prepare us for actinium, because before nuclear technology existed, there was no encounter to prepare for. The people working with it today are the first generation to do so, and that is precisely why protection when handling actinium is not bureaucratic box ticking. It is a matter of cellular survival, literally. There is documented evidence of what happens when that control slips. 1992. The Soviet Union had just collapsed. Organizational chaos, financial chaos, administrative chaos, all at once. Institutions were closing or changing status. Funding was cut off overnight. Scientists who had spent decades working with radioactive materials under strict, controlled conditions suddenly found themselves without salaries, without security, and without clarity about who even owned the equipment they'd been working with. In this context, several actinium samples from Soviet scientific programs simply vanished from the paperwork. Not stolen in any classic sense, just lost in the chaos of institutional reorganization. Some records didn't survive the transition. Some materials were transferred incorrectly. Some physically disappeared, along with the people who were the only ones who knew where things were kept. The International Atomic Energy Agency documented similar incidents with various radioactive materials across the former Soviet states throughout the 1990s. Actinium appeared on that list. In small amounts, but it appeared. Most cases eventually resolved when materials turned up in the back corners of laboratory storage rooms, in containers with wrong labels or incomplete documentation. A few cases remained open. This is no cause for panic, since the quantities were microscopic, and using actinium without specialized infrastructure is practically impossible. But it is a vivid illustration of a simple truth. Actinium does not forgive carelessness, not in the laboratory, and not in an inventory system. Actinium sits at number 89 in the periodic table, and it gives its name to an entire family of elements, the actinides. These are 14 elements running from thorium to lawrencium, arranged in the bottom row of the periodic table. Uranium, plutonium, curium, californium, americium, all actinides. All of them carry their family name from actinium. What unites the actinides is a shared electron structure. In all of them, the 5F subshell is being filled. This is what drives their chemical similarities, and it's precisely why actinium is so indistinguishable from lanthanum in solution. Lanthanum heads the lanthanides, an analogous family in which the 4F subshell fills instead. The chemical mimicry between actinium and lanthanum is not a coincidence or a quirk of nature. It's a consequence of deep structural symmetry in how atomic electron shells are organized. When Mendeleev constructed his table in 1869, he knew nothing about the actinides as a family. The concept of F electrons came later. He simply arranged elements by atomic weight and chemical properties, and the table revealed the symmetry on its own. Actinium and lanthanum turned out to be similar not because anyone decided they should be, but because quantum mechanics is built that way. Nature repeats its patterns. The periodic table is not a reference book. It's a map of those repeating patterns. And actinium is one of the most striking examples of how deep those patterns go. When scientists in the 20th century began synthesizing transuranium elements, plutonium, curium, berkelium, californium, the chemistry of actinium helped predict how they would behave, because they're all one family, operating by the same rules. Actinium isn't just an element, it's the heading of an entire chapter in a book we're still reading. That might sound philosophical, but it's simply true. There's a moment in the history of any scientific idea when it stops being just an idea and becomes something that changes real lives. For actinium, that moment came in oncology clinics, and what's happening there right now deserves a serious conversation. Not an abstract one, but a very specific one. To understand why oncologists call actinium a revolution, let's first look at the mechanics of its decay. The details here are particularly interesting, and the devil is entirely in them. When a nucleus of actinium-225 decays, it doesn't end with a single blast of radiation. It triggers a cascade, a sequence of 4 consecutive alpha decays, each one releasing a heavy particle. 4 powerful strikes in a row from a single original atom. What does an alpha particle actually mean in practice? It's 2 protons and 2 neutrons flying together at enormous speed. It's heavy by the standards of nuclear physics, it's charged, and it slows down very quickly in living tissue, within just 5 to 7 cell lengths. And it's precisely during that deceleration that the key event happens. The particle transfers an enormous amount of energy to the cells in its path. It literally cuts the DNA double helix in multiple places at once. This is not damage a cell knows how to repair. It's not a scratch. It's the destruction of the load-bearing structure. The cell stops functioning and dies. Most radioactive isotopes used in clinics today deliver just 1 or 2 such impacts. Actinium-225 delivers 4, 2 to 4 times more effective. That's not marketing language, that's physics. And here's the most important part. The path of an alpha particle through living tissue is only 5 to 7 cells long. On the scale of the human body, that's almost nothing. But that short distance is the entire point. Neighboring healthy cells stay safe because the destructive force simply doesn't reach them. Enormous power, hitting precisely where it's aimed, without touching anything a few micrometers away from the impact zone. Compare that to conventional chemotherapy. There, a drug travels through the entire bloodstream and attacks any rapidly dividing cells, cancerous and healthy alike. Hair loss, nausea, damage to mucous membranes, immune suppression. All of these side effects exist because the drug doesn't know how to choose. It has no destination. It just goes everywhere. Actinium knows how to choose. More precisely, the molecule carrying it does. Actinium just fires wherever it's been delivered. Now, the specific story I promised. Not abstract oncology, but a real clinical path that changed medicine's relationship with this element. 2013. German oncologist Klaus Kopke and his team at the Heidelberg University Cancer Center began the first clinical work with actinium-225 on patients with metastatic prostate cancer. Final stage. Chemotherapy had run out of options, hormone therapy too. The standard protocol ends where the list of drugs ends. After that, it's palliative care and survival statistics nobody wants to read aloud to the patient. The team began using actinium-225 paired with a molecule capable of finding a specific protein on the surface of prostate cancer cells. That protein is called prostate-specific membrane antigen. It's present on virtually all prostate cancer cells and largely absent from healthy cells elsewhere in the body. A near-perfect target, which is rare in oncology, where tumor cells often disguise themselves as healthy ones. The molecule finds the cell carrying that protein. It attaches. Actinium, riding along on the molecule, ends up right next to the target and triggers its 4-strike cascade. The results of the first clinical observations were so unexpected that colleagues initially greeted them with open skepticism. That happens in medicine. When data looks too good, the first reaction is that something must be wrong with the methodology. In some patients who, by every prognosis, had only months to live, tumors began to shrink. Cancer marker levels dropped. Pain decreased. Some patients lived significantly longer than statistics had predicted. An honest clarification is needed here, because it's easy to confuse two similar but distinct approaches. In 2022, the New England Journal of Medicine published results from a large trial on targeted prostate cancer therapy. But that trial used lutetium-177, a different element, a beta emitter, with the same carrier molecule concept, but a different physical mechanism of action. That treatment received regulatory approval and became the first approved therapy of its class. Actinium is next in line. Clinical trials are ongoing, data is accumulating, and preliminary results are convincing. But honesty requires keeping these two substances in separate sentences. For actinium-225 specifically, Phase 1 and Phase 2 trial data published by Kopke's group and several other teams between 2015 and 2023 showed that in patients with hormone-resistant prostate cancer who had exhausted standard options, actinium therapy produced meaningful reductions in cancer marker levels and measurable tumor shrinkage. In some patients where the disease was considered terminal, the treatment response was unexpectedly durable. This is not science's final word. Trials are continuing. But the direction is convincing enough that several major pharmaceutical companies have put serious money into it. This was not a miracle. This was physics put to work in medicine. The principle of actinium therapy is always the same. Take a molecule that can find a specific type of cancer cell, attach actinium-225 to it, and send it into the body. What changes is the carrier molecule. Each cancer type requires a different carrier, targeting a different marker on the cell surface. Neuroendocrine tumors are a rare group of malignant growths arising in hormone-producing cells, the pancreas, lungs, gastrointestinal tract. They grow slowly but metastasize to unexpected locations. For these tumors, researchers have developed molecules that find specific receptors on their surface, known as somatostatin receptors. Clinical trials of this approach using actinium are underway at several European centers, with promising early results. Pancreatic cancer is among the most aggressive forms of the disease. 5-year survival for the metastatic form sits at just a few percent. Standard chemotherapy extends life by months, not years. Research groups in the United States and Germany are testing actinium paired with molecules targeting specific proteins on these cells. Early-stage trials, but the fact that such trials are happening at all already says something. Acute myeloid leukemia, a blood cancer that responds poorly to treatment at relapse, is being studied by several groups in the United States and Israel using actinium paired with molecules targeting specific antigens on the surface of leukemic cells. Everywhere, the same physics, the same principle, different carriers, different targets. Actinium-225 is becoming a platform that can be redirected at virtually any cancer type, as long as the right carrier molecule is chosen. Platform is the key word here. Not a drug for one specific cancer, but a universal tool that can be calibrated to match a specific task. However, between where we are now and making this technology truly widespread, there stands a physical problem. It's called the recoil problem, and it rarely gets discussed outside specialized laboratories. Time to change that. When an actinium nucleus ejects an alpha particle, the same thing happens as when a powerful rifle is fired. The gun kicks back. The nucleus itself experiences a violent recoil. The energy of that kick is 100,000 times greater than the strength of any chemical bond known to science. As a result, the bond between actinium and its carrier molecule snaps instantly. The carrier effectively flies apart. The newly formed atom, now a different element entirely, francium, a decay product, is left to drift freely through the body. And it still has 3 more transformations ahead of it. Francium becomes astatine, astatine becomes bismuth, and at each step the nucleus gets that same reactive jolt again. Each new transformation knocks the atom away from where it's supposed to be. Some decay products leave the tumor zone and get carried through the bloodstream. Bismuth-213, for example, can accumulate in healthy tissues, particularly the kidneys and bone marrow, causing unwanted irradiation there. This doesn't make actinium useless. The clinical results already seen in cases where medicine had previously given up are genuinely impressive. But the recoil problem is an engineering challenge that must be solved before this promising method can become a fully safe, widely available therapy. Right now, in several laboratories around the world, including at the Massachusetts Institute of Technology and at the Heidelberg Cancer Center, researchers are developing nanoscale containers. The idea is to enclose actinium inside a tiny cage made of a material strong enough to keep the decay products trapped inside, yet small enough to reach a tumor. The outside of the container carries the targeting molecules that find cancer cells. Inside is actinium with its entire cascade. The container arrives at the target. Actinium fires all 4 times, and the daughter products stay trapped inside rather than scattering through the body. This is still at the laboratory stage, but it's a viable direction, and several groups have already reported encouraging results in cell cultures. The medicine exists. The target is known. The physics works. The only problem is that the substance doing all of this exists on this planet in quantities that would fit in a thimble. And it can only be obtained in one way, one you almost certainly wouldn't guess. There is a place in the American state of Tennessee that ordinary people don't get to enter. It's called Oak Ridge, a small city, around 30,000 residents. Nothing unusual on the outside, quiet streets, ordinary houses. But this is where, in 1943, in the middle of the Second World War, as part of the Manhattan Project, scientists began enriching uranium for the first atomic bomb. A secret city that appeared on no map. Workers didn't know what they were producing. They were told only what was necessary for their specific task at their specific station. Nothing more. 80 years have passed. Oak Ridge is still operating, and today its reactors produce Actinium-225 for oncology clinics around the world. Every few weeks, a small shipment leaves the facility, a specialized container with lead walls and accompanying paperwork as thick as a brick. The quantity of material inside is microscopic. The price is astronomical. For a long time, the main source of Actinium-225 was thorium-229, an isotope that accumulated in American research laboratories during the 1960s and 70s during studies on thorium-based reactors. Thorium-229 decays slowly and produces Actinium-225, drop by drop. World reserves of thorium-229 are limited, and they are gradually being consumed. This is exactly why, in 2019, the United States Department of Energy announced a program to expand actinium production by irradiating radium-226 in reactors. At the same time, similar programs launched in Canada at the Chalk River Laboratories and in Russia at the Institute of Physics and Power Engineering in Obninsk. 3 countries that spent the middle of the 20th century racing to build nuclear weapons are now competing to produce actinium for cancer treatment. History takes unexpected turns, sometimes good ones. Global production of Actinium-225 has been growing, but it still falls far short of the potential demand. The entire world's medically usable supply, until recently, amounted to just a few curies per year, enough to treat a few hundred patients worldwide. Meanwhile, in the United States alone, more than 250,000 new cases of prostate cancer are diagnosed every year. The gap between what exists and what's needed is enormous. And here is something worth pausing on. The cost of 1 gram of actinium is estimated in the tens of millions of dollars. This makes it one of the most expensive materials in human history. But this isn't market speculation or artificial supply constraints. It reflects the true cost of production. Specialized reactors, complex separation chemistry, strict purity requirements, and a short shelf life due to radioactive decay. Every microgram of Actinium-225 that reaches an oncology clinic has traveled a path that most pharmaceutical supply chains cannot even imagine. This is not just a drug, it's the physics of the Cold War, reforged into 21st century medicine. Marguerite Perret, French nuclear physicist. In 1939, she was working at the Radium Institute in Paris, the very institute founded by Marie Curie. Curie had been dead for 5 years by then, but her work lived on in the institute, and Perret was part of that work. She was doing what today would be called painstaking research, mapping the complete decay chain of Actinium-227, tracking exactly what it transformed into at each step. And in the data, she found something she hadn't expected. One of the decay products didn't match any known element. It didn't resemble anything in the periodic table. Perret ran additional measurements, repeated the experiments, checked her equipment. She was certain this was a new element. Element number 87. She named it francium after her homeland. That element will definitely get its own episode. Here's what makes this discovery remarkable. It was the last element to be discovered through the study of natural radioactive decay, before the era of synthesizing artificial elements in accelerators began. After Perret, new elements would be created in laboratories, not found in nature. She closed the era of natural discoveries. And she did it as a woman working in the shadow of a legendary predecessor, in the institute that predecessor had built, 5 years after her death. Marguerite Perret became the first woman elected to the French Academy of Sciences in 1962. 23 years passed between the discovery of francium and that recognition. For a man with the same discovery to his name, that path would have been shorter. But that was the time she lived in, and she walked it all the way to the end. Let's shift direction for a moment and head to the bottom of the ocean. There's a question that geologists and oceanographers ask constantly, And the answer is worth billions of dollars in the most literal sense. The question is, how old is this rock? Not approximately, precisely, with an error of fractions of a percent. The answer determines where to drill, how to read the geological history of a region, and how to understand past climate shifts. Most people have heard of radiocarbon dating. Carbon-14 decays at a known rate. You measure how much is left and calculate the age. It works up to about 50,000 years. Beyond that, so little carbon-14 remains that the measurement becomes meaningless. But geologists often work with rocks hundreds of millions of years old, or marine sediments ranging from 100,000 to several million years in age. Carbon is useless there. For a specific range of ages, one of the most precise methods available is dating based on the ratio of uranium-235 to actinium-227. Here's how it works in practice. Uranium-235 and actinium-227 are linked by a decay chain. Uranium inevitably produces actinium as an intermediate product. If a rock or a coral skeleton formed under conditions where uranium and actinium could separate, for instance during the crystallization of a mineral from seawater, then at the moment of formation, the ratio of these two isotopes was a specific, known value. Since then, it has been changing according to precisely predictable laws of radioactive decay. Measure the current ratio with a mass spectrometer, and you can calculate how long ago the rock formed. This method is especially valuable for dating marine carbonate sediments and corals between a few thousand and a few 100,000 years old. Exactly the range that's critical for understanding the climate of the Pleistocene, the last ice age, and everything connected to it. When did the glaciers retreat? When did sea levels change? How quickly did it all happen? A small coral skeleton sample, a few hours in a mass spectrometer, and you know its age to within a few hundred years out of hundreds of thousands. But actinium does something even more interesting in the ocean, and it connects directly to the climate of today. Actinium-227 slowly seeps into seawater from seafloor sediments, drop by drop continuously at a constant rate. Its concentration in the water column depends directly on how long ago that water last rose from the depths to the surface and mixed with other water masses. The longer the water has sat at a given depth without mixing, the more actinium has accumulated from the sediments below. The more active the mixing and exchange with other water bodies, the less actinium you find. Oceanographers measure actinium concentrations at different depths and get a map of how water moves through the deep ocean. Actinium acts as a natural tracer that adds itself to the water at a known rate. Knowing the rate of input and the measured concentration, you can calculate how long that water has been sitting at that depth. Actinium data has been used in major international studies of deep water circulation in the Atlantic Ocean. If you've heard of the slowdown of the Atlantic meridional overturning circulation, the global conveyor of warm and cold currents that regulates the climate of Europe, that's exactly the process actinium helps to study. A slowdown of this system could mean sharp cooling across Western Europe, even as the rest of the planet warms. This isn't a distant hypothetical. It's an active area of climate research, and actinium is one of the measurement tools being used. A metal that glows blue in a laboratory is simultaneously serving as a clock on the floor of the Atlantic Ocean. It measures not seconds or years, but the centuries that deep water has spent without rising to the surface. One element, and this range of uses. It would be hard to invent. Now let's talk about thorium energy, because here too, actinium turns out to be unexpectedly significant, even though it's rarely discussed outside a narrow circle of specialists. You may have heard of thorium reactors. The idea of using thorium as nuclear fuel has been discussed since the 1950s, but right now it's attracted renewed attention in several countries simultaneously. Here's the core concept. Thorium-232 cannot sustain a chain reaction in a reactor on its own. But if you bombard it with neutrons, it transforms into uranium-233, which fissions extremely well. Thorium becomes fuel through an intermediary. The thorium cycle has several fundamental advantages over conventional uranium reactors. There is 3 to 4 times more thorium on the planet than uranium. A thorium reactor produces far fewer long-lived radioactive waste products. The isotopes it generates decay over hundreds of years rather than tens of thousands. And the thorium cycle makes it nearly impossible to produce weapons-grade material, which makes it strategically attractive from a non-proliferation standpoint. This isn't an advertisement for thorium reactors. These are simply facts about comparative physics. Where does actinium come in? During the operation of a thorium reactor, protactinium-233 inevitably forms as an intermediate isotope in the chain from thorium to uranium. It then decays into uranium-233, the target fuel. But protactinium has a property that creates an engineering problem. It absorbs neutrons, slowing the reaction and reducing efficiency. Some thorium reactor designs propose continuously extracting protactinium from the reactor core and holding it separately until it decays into useful uranium-233. The chemistry of that separation process, working with a molten salt coolant, involves actinium chemistry in a supporting role. Because actinium, lanthanum, and protactinium behave similarly in certain chemical systems, and understanding actinium's behavior helps build models for working with protactinium. China launched an experimental molten salt thorium reactor in 2021, the first working reactor of that type since 1969. India has officially incorporated thorium reactors into its long-term national nuclear program. If thorium energy becomes a reality over the next few decades, actinium will be not just a medical tool and a geological clock, but also part of the chemistry that keeps reactors powering cities. One element: medicine, geology, climate science, and the energy future. This is not a coincidence. It follows from the fact that actinium occupies a special position in nuclear chemistry, a position where several fundamentally important processes converge at once. And now, the finale. We return to Przybylski's star. We started there, and will end there, because it gives this entire story the right sense of scale. After more than 60 years of observation, the mystery hasn't been resolved. It has deepened. New spectroscopic data collected with modern telescopes confirms that the star's spectrum contains not only actinium, but other short-lived elements as well: polonium, radium, protactinium. An entire collection of isotopes that have absolutely no business being there according to any standard model of stellar evolution. This is not an isolated anomaly that could be attributed to measurement error. It's a consistent, reproducible pattern. It's there, and it doesn't disappear under closer observation. It gets clearer. The island of stability hypothesis becomes more compelling and more significant in light of this. If the interior of Przybylski's star really is hosting the decay of long-lived superheavy nuclei, then this star is a natural demonstration of physics we cannot reproduce in a laboratory. It's showing us something we can theoretically predict, but cannot experimentally confirm. The heaviest element humanity has ever created, organoson, number 118, survives for about 5 milliseconds. And that already took decades of work to achieve. Somewhere, 380 light-years away, something with more than 120 protons in its nucleus has been quietly existing for billions of years. If that's confirmed, the periodic table doesn't just need to be extended. It needs to be reconsidered in light of elements whose existence we can only guess at. Przybylski's star may turn out to be the most important astrophysical object we're currently observing. Not because it's beautiful or powerful, not because it's close or far, but because it shows us that physics has a corner we cannot see, an entire region of reality we only know exists because otherwise this star makes no sense. Astrophysicists continue their observations. Next-generation telescopes will produce data that either confirms the island of stability hypothesis or raises questions even more uncomfortable than the current ones. The star isn't in any hurry. It was there long before us, and, by all indications, will be there long after. When DIDN named the element actinium in 1899, from the Greek word for ray, he meant radiation, radioactivity, a glow in a darkened laboratory. A logical name for an era when radioactivity had only just been discovered and seemed like the defining property worth commemorating. But if the name were being chosen today, perhaps a different word would do. because Ray is only the most visible part of the story. Actinium is a deceiver that impersonated lanthanum for half a century and led an entire generation of chemists astray. It's a factory that continuously produces and destroys the rarest element on Earth inside itself. It's a geological clock on the floor of the Atlantic Ocean, measuring centuries of water movement. It's a precision weapon in an oncology clinic, hitting its target where every other method is given up. It's the heading of an entire family in the periodic table. It's a key to the chemistry of thorium reactors that may be powering cities in 30 years. And it's an unsolved puzzle in the spectrum of a distant star, still giving no answer, and for that reason, making physics more interesting than any invented story. One element, 89 protons, and enough roles to fill a separate story for each one. We tend to think of the periodic table as something finished. 118 boxes, all discovered, all known. Memorize them for the exam. But Actinium says something different. Every time things seem clear, it adds another question. About the star, about the ocean floor, about how 4 billion years of evolution left us completely unprepared to meet it, about how the periodic table is not an answer. It's a list of questions, most of which we haven't even thought to ask yet. A blue light in the dark, a metal that melts from its own existence, a ghost that spent half a century hiding under someone else's name, and a star 380 light-years away, shining something at us we still don't understand. Element number 89. Thank you for watching all the way to the end. I want to ask you something. What do you make of the last resort hypothesis I mentioned at the beginning of the video? Share your thoughts in the comments. I genuinely love to read what you think. See you next time on Ashes of Stars.